we're going to have a chat here about resistors that are connected in parallel. And parallel means next to each other. They're like parallel lines. Could be how you connected elephants. If you tied all their trunks together and all their tails together, you'd have your elephants connected in parallel. First of all, let's think about the voltage on the resistors in parallel. Voltage, remember, we measure across the resistor, and so I've drawn a voltmeter measuring across each of those resistors in parallel to it. And so V1 measures the voltage of R1, V2 measures R2, and V3 measures R3, and V total measures across the whole lot. If we look at where the legs of each of these voltmeters are connected, we can see that the left-hand leg of V1, V2, V3, and in fact V total, are all connected to the same place, because these blue lines here, they're just wires with no resistance, negligible resistance. And it's the same for the right-hand legs. They're all connected to the same place as well. And so from that, hopefully we can tell that we're going to get exactly the same reading on each of those voltmeters. In fact, V1 is V2, is V3, is V total. And so the voltage on all the components in parallel is the same. Let's think about current. Our total current's going to come trundling in from the left-hand side. There it is, total current. And it gets to this junction here, and it's going to split 3 ways. If one of these resistors is smaller than all the others, more current is going to go through that one because it's a path of lower resistance. And current always follows the path of least resistance, or most current goes through the least resistance. And so we're going to have 3 different currents that are all split out of that one main current. There they are, I1 going through R1, I2 going through R2, and I3 going through R3. We can see from that I1 plus I2 plus I3 must be I total, and so in a parallel circuit, the currents through each of the resistors in parallel adds up to the total current. Ohm's law. V equals IR. We can rearrange that to R is V upon I. R total is V total upon I total. And we can rewrite that as R total is V total upon I1 plus I2 plus I3. Still hard to work with. Let's flip both sides the other way up. So what we've got here, look, I flipped everything upside down. Instead of R total, I've got 1 over R total. Instead of V total over I1, I've written I1 over V1. And it's okay to substitute in V1 instead of V total, because V1 is V total, is V2, is V3. And so 1 over R total is I1 over V1, I2 over V2, I3 over V3, and V upon I is R, so I upon V is 1 upon R, I1 on V1 is 1 upon R1, I2 on V2 is 1 upon R2, and I3 on V3 is 1 upon R3. And so this brings us to an equation that we can use to find the total resistance in parallel. 1 upon the total resistance is 1 upon R1 plus 1 upon R2 plus 1 upon R3. When you do use this to solve problems, make sure that you remember you're solving for 1 upon resistance. And so once you've plugged your numbers in, don't forget you need to flip it back the other way up in order to get the correct answer. We might do an example on that. Here we are. How about 3 resistors connected in parallel? A 12, a 20, and a 30. I chose those numbers because they work out nicely, as you'll see in a second. we're going to start by writing out our equation. There's our equation for parallel resistors. 1 upon total resistance is 1 upon R1 plus 1 upon R2 plus 1 upon R3. Let's plug in the numbers. Now, if you were ever one of those students who used to bother your maths teacher by asking them why you need to learn to add fractions, where am I ever going to use this in real life? Here's the answer, right? Adding resistors in parallel. So 1 upon R total is 1 upon 12 plus 1 upon 20 plus 1 upon 30. We can see straight away it's ugly. We can't just add them together. We need a common denominator. A good common denominator for this situation is 60, because there's 5 12s in 60, 2 30s, 3 20s. 60 works beautifully. Let's swap these over to a denominator of 60, or if you've got one of those flash calculators, you can just use the fraction button. There we go. I've multiplied the top and the bottom of that first one by 5 to get 5 60ths. The top and the bottom of the second one by 3 to get 3 60ths. And the top and the bottom of the second one, the last one, by 2 to get 2 60ths. Now we can just plug those numbers together. 5 plus 3 plus 2 is 10 60ths. Now this is the point where we have to be careful to remember that what we've calculated is not the answer. We've got 1 upon R total to get the answer. Now that we've got fraction equals fraction with no plus signs hanging around in there, we're going to flip both sides of that equation the other way up. Look. R total over 1, we don't bother writing the over 1 part though, is 60 over 10. 60 divided by 10 is 6. And it's one of those interesting facts about parallel circuits that the total resistance is always less than the smallest of any of the resistors. And so you can know that we've got a reasonable answer because the smallest resistor was 12 and our answer is less than 12. And that rule is always going to work. It doesn't matter if this one's 1,000,000 ohms, the answer is still going to be less than 12. And the opposite applies with series circuits. In a series circuit, the total resistance is always greater than the greatest resistance. And that's just because we're plussing all the numbers together. But because we're plussing the inverse of the numbers here, unusual and unexpected things happen. It's not really unexpected when you think about it. But it's not unexpected because 12 there's got 12 ohms resistance there, and as well as having the 12 as an option, there's 2 other options, and so those options are going to reduce the overall resistance. The more pathways that we provide for the current to flow, the lower the resistance. And so it actually does make sense that our total resistance is less than any of the individual resistors.